Welcome to this lecture series in real analysis. We are starting a new module, and in this module we will be discussing the notion of the series of functions, and in particular we will be developing the theory of exponential and logarithmic functions, two of the most important functions in analysis. And we will require the knowledge of, well, so many prior lectures, almost everything, but in particular we will need to know about infinite series and the things discussed in the previous module, which was sequence of functions. In particular, we discussed pointwise convergence, uniform convergence, and the Cauchy criterion for uniform convergence. We saw that pointwise convergence was a weak notion in the sense that it did not preserve properties in the limit that we would like to be preserved. But uniform convergence was a fairly strong notion, and it does satisfy our needs in many respects. Anyway, so let's proceed. So what is the definition? You can guess the definition of a series of functions. Just like given a sequence of functions, you can correspondingly form an infinite series. Given a sequence of real numbers, you can correspondingly form an infinite series of real numbers. Here we are given a sequence of functions. So naturally, the definition of the corresponding series of functions is, well, just this formal symbol. Just the symbol. This may not be a meaningful function on the domain. So, for instance, if you feed it some x from the domain S, if you consider this particular infinite series, this is a series of real numbers. Once you've chosen an x from the domain S, this is a series of real numbers. It may or may not converge. If it happens to converge for each point x in the domain, then fine, then we declare that this series is a convergent series of functions, otherwise not. So that is the next set of definitions. So we have a sequence of functions. We say that the corresponding series of functions is convergent, or it converges if, as we said above, this series of real numbers converges for each x in the domain. So then it is a bona fide function from the set S to the real numbers, if this happens. Okay, we say it converges absolutely if, again, you can guess the definition, it converges absolutely if this converges. Right? Natural definition. And we say it converges uniformly if the sequence of partial sums of the functions converges uniformly. Right? So for each n, we can define a function Sn, or maybe I'll write little sn. Maybe it's a bad symbol. Let's call it Gn. Gn is the sum of first n functions, right? This is a genuine function. There is no issue of convergence or anything. So we get a sequence of functions. If this sequence of functions converges uniformly, then we declare that this series, this series is uniformly convergent. Clearly, uniformly convergent implies convergent. That's an exercise. If you have a uniformly convergent series of functions, it is clearly a convergent series of functions. Note that the notion of convergent series is same as the sequence of partial sums being pointwise convergent. Right? So in fact, we could have perhaps called it pointwise convergent series, but okay, it's clear, I think. All right, so some very simple definitions or very natural definitions. Let's look at one example. So for each whole number, not just natural number, but each whole number, we define a function fn via this rule. So for each real number x, this is the output, and then we can form the corresponding series. And it so happens that, well, that this series converges for each x. And in fact, in fact, the series has this value. I mean, the series, whatever this function is, behaves like this. We have a explicit description. And it's a very simple exercise as to why. So if x is 0, then each fn takes the value 0. So basically, fn of 0 is 0 for each n. And clearly then, this thing will also be 0. So the first line is justified. For the second line, if x is non-zero, then this summation is this summation, which is same as that. And here we have a geometric series where the common ratio is, or the common ratio is less than 1 in the absolute value. And that's it. If you just sum up this geometric series, you will get this expression. Very simple exercise. Just an example of a pointwise convergent series of functions. You can think if this is an absolutely, if this is a uniformly convergent sequence of functions. Think about that. Hint, this is a discontinuous function. Okay. So fine, this is an example, and let's maybe finish this lecture by one last thing. So this is a criterion to decide if a given sequence of functions is uniformly convergent. Given series of functions is uniformly convergent. So we are given a sequence of functions, then we form the corresponding series. And suppose there is a sequence of real numbers such that each fn is uniformly bounded by mn, which means that the bound is not sensitive to the input x. So each fn is uniformly bounded by mn, and the mn's sum up to, or the series of mn's is convergent. Each mn is certainly a non-negative number, and assume that that series is convergent. So then the series of functions converges both absolutely and uniformly. So let me justify uniform convergence. It is just a matter of applying Cauchy's criterion. So here is the proof. Proof for uniformity. So all we need to do is, we need to talk about this thing. So yeah, so what does it mean to say uniform convergence? If you have S or Gn defined as this, we want to see if this is a uniformly convergent sequence of functions. But to do that, by applying Cauchy's criterion, what we need to check is if one can show that this thing can be uniformly bounded by epsilon, provided m and n are sufficiently large. So what is this quantity? This quantity is nothing but, suppose m is at most n. So this quantity is nothing but summation k from m plus 1 to n. Maybe take m strictly less than n, otherwise I freak out. Although technically nothing is wrong. So we are interested in this thing, right? But this is bounded by triangle inequality. Now we use this estimate that is given to us. But this is indeed arbitrarily small if m and n are sufficiently large because of the convergence of the series of mn's. That's it. There is no point me writing a full formal proof of this, because by now we should be mature enough to follow these things without a full formal technical gory proof. This should be enough. So that's it. That is the proof for uniform convergence. For absolute convergence, nothing. Just replace fn by mod fn. Nothing changes. So This is a very simple test. It's called Weierstrass M-Test. It's simple, but it is useful. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.